Hello YouTube, De-bodgery here, aka Richard Gumthaw on Facebook. Welcome to EV Components Review. Please like, subscribe, comment, things like that in the videos, please. That helps my channel grow. This is the power stage for a Surron controller. And there used to be two connectors that were right here. Unlike the EBMX power stage, they just simply ripped off of the solder pads rather than pulling up traces and stuff. So this is better, in my opinion. This is still a metal coarse printed circuit board, and there's some damage to it, which I'll show in a while. But yeah, these small pads, they didn't tear up like I expected, and the potting basically is what did it here. They were so bonded into the pin headers, the connector pin, these right here, that they would not come out. Didn't matter how much heat I applied, because I did, like I did with the Tolaria controller, I put this in my toaster oven too to get it hot. And yeah, even with just pulling it right out and then immediately working on these things, those pins would not come loose. And instead, the solder joints failed. So yeah, that's a better thing to have. I can solder that back down again if I want. But yeah, there's one of them. Yeah, no real harm done here. Just got to solder back down again if I wanted to fix it. But I don't care. Alright, so these are your gate drivers. And these are single channel gate drivers. If you look at, like, say, the Tolaria, you have kind of the same setup. I think that's... let me pull up that board real quick. No, you don't have the same one. So, yeah, on the Tolaria board, you had an 8-pin gate driver, but the one gate driver handled both the low side and the high side MOSFETs. And in the Surron, you don't. You've got 6 of them, and you only have 3 phases. So, like these over here, like say all driving high sides, and those ones over there all driving low side MOSFETs. But each one of these is only one or the other, either a high side or a low side MOSFET gate driver. They're all the exact same part number. They're all the same, whatever this, IR2127s, I think it is. Let me look at that up real quick. I've got that part number here. Wherever it is. There it is. Yep, so that's an international rectifier part, an IR2127. And they're a single channel driver, which is basically what I just said. They can't do high side and low side on each chip. They can only do one or the other. So yeah, that's why there's 6 of them. And again, you'll see the same thing as before. You've got a couple of MOSFETs here for boosting current to the gates. So these MOSFETs must take a fair bit of gate current to kick them over. However, unlike the other one, these are 200 milliamps, and I think the ones that were on the Tolarias were 100 milliamp. Anyway, I don't remember for sure. But yeah, they're wanting to boost that current up to the MOSFET gates a little bit. So you've got some MOSFETs over here to kind of boost that power up some. They do have some ceramic caps in them, like this. And I believe the Tolaria did as well, just not quite as much. But yeah, this is high frequency filtering right here across battery plus to battery minus. So it's kind of nice that it's right there at the gate driver. Let's see what else I want to show you here in the gate section. It's pretty much everything that's there. Otherwise, yeah, each one of them is all the same. You might notice these things right here. So these are a 0 ohm resistor. You could say this is a wire for all intents and purposes. And keep in mind, this is a metal core printed circuit board. So all the traces have to be on the surface here. There can't be layers. Otherwise, you would create insulation, basically a thermal layer that doesn't conduct heat very well. And so sometimes you have to get stuff from point A to point B, but you can't do it inside the board. You have to do it on the surface. And that's what these are. These are jumpers. So there's a trace here that it needed to go over to something else. So it has to jump over those 2 traces to get there. So there's that. And then it comes over to here. And then it's got to jump again to get over there. And then it's got another trace here. So then it jumps again to get over to this leg right here. And here's the same thing. Here's another one of those things. It has to jump over that same little trace right there to get over here. And then right there, it's got to jump over wherever it is, 2 of them, to get to here, and then finally you can get over to this MOSFET, this gate driver chip right here. So yeah, these little zero resistors here, they are literally a jumper wire for all intents and purposes, just a surface mount one. Yeah, and you can see a couple more of them right there. But yeah, that's a fairly common thing that you'll run into circuit boards, especially like in single-sided stuff like this, where you can't put layers inside the board or have circuit traces on the bottom side. Yeah, you'll see like a little jumper like this to get that to happen. Anyway, let's look at some other stuff. So right here, this is your battery minus bus. So it screws down right here, and then you had 4 shorter studs like that. Oops, get that on camera. There we go. And they were soldered down here. And these are threaded on the inside, which you can kind of see in there. Yeah, you can see the threads in there. And I believe, because these came up really easy, when I was de-potting, in fact, all 5 of these did. They came up super easy. When I was taking up the really rock-hard potting, I'd heat it up. But these little standoffs, these little threaded standoffs, they came up super easy. They literally pulled up with no effort whatsoever. Hot potting, which was fairly flexible at the time, and it pulled up all 5 of those without any stress at all. And as you can see, these things are pretty short, and they're not ribbed or anything like that, so they shouldn't have really like gripped into the potting all that well. My thinking is that they were never soldered down particularly well anyway. Like right here, you see that little shiny spot? That's like the only place it was soldered down, I think. Or this one here, there's a little shiny spot on there. I was like, that was the only spot. Let me flip this thing upside down so we can look at the bottom side of it. See if I can't make it focus right there. There we go. So it looks like it might have been soldered all the way around. It's kind of hard to say. You might go back to there. There we go. Yeah, it might have been soldered all the way on the bottom of that, but yeah, it doesn't have very much, that's for sure. This is a fairly small area. There's no overflow of solder anywhere. Yeah, it's not a whole lot of surface area, and I think probably pulling it up to the logic board stressed those solder joints and pulled them loose, because they weren't held down by anything that I could tell. They literally just came right up with the potting, and they shouldn't have done that. Not for a smooth little cylinder like that. They should not have pulled up that easily. And even this center one here, which is ribbed for your pleasure, I think it was that one right there. Yeah, that one came right up too. Yeah, that one was super easy to come up. So as you can see, this little bit of area didn't hold this stud very well. But other studs did stay put. So like this one right here. So this is on, that's a phase bus right there. And that one, it didn't come loose. It's nice and snug. It didn't move. So that one stayed put. Over here, there's another phase bus. Again, that one is nice and solid. It's a different height one. And here is your other phase bus right here. And the same thing. That one's nice and solid. Yeah, and you can see like the copper in here between the MOSFETs. Really like seeing, more than just circuit traces in there. The gaps are fairly small here, and this isn't a very powerful controller, so it's probably enough. But still, yeah, I like seeing copper in boards. Copper reinforcing, because that's really how you should do it. You see this little resistor right there that goes over to this leg of the MOSFETs, and that is your current limiting resistor for this MOSFET, and you can see the same one there for that one, and the same one there for that one. Yeah, you can see it for all of them. So this is very consistent, unlike the Teleria, which is kind of weird. I don't know why they did it the way they did, but yeah. Anyway, so you've got 12 MOSFETs per phase. These are not particularly powerful MOSFETs, so these are made by, I think they're Infineon. Hold on a second, I got the part right here. Just got to find it again. Yeah, there we go. So yeah, they're an Infineon MOSFET, and they are an 042N10N, which you can see on the part, obviously. But yeah, they're a 100 volt component. The internal resistance is pretty high, 4.2 milliohms. For a MOSFET, that's pretty high, especially for a 100 volt part. Yeah, not exactly the best ever. And their current rating is pretty low, just 137 amps per MOSFET. So yeah, they're weak, high internal resistance, not very efficient MOSFETs. Don't know why Surron picked them. Maybe they were cheap or something. But yeah, when I saw what they were, I was like, huh, that's weird. And the other thing is their tolerance to heat is quite low too. This package is good for 500 watts worth of heat. That's a lot of heat. You know, that's basically 1/3 the power of your typical blow dryer or your typical little floor heater. And this is a 500 watt package, but yet this specific MOSFET, it can handle but 200 watts worth of heat. So it's a pretty weak MOSFET. You know, this is probably something that Infineon was making in mass like 10 years ago, and they just still make it. I don't know. You can see the date code on there, 2018, you know, 0528. So this wasn't made that long ago, but yeah, these are kind of weak-ass MOSFETs by today's standards. You know, and that's even from Infineon. Anyway, let's see, what else do I want to show you? Oh yeah, right there. So, this is a bit better than you see on the Teleria. So you've got two ceramic capacitors here. And, you know, it's pretty close to the MOSFETs. So you got one set of MOSFETs here, and there's another phase right there. So that's kind of in the right place for that. And then down here you've got two more of them. Yeah, and that's like all of the ceramic caps that are on here. So it's an inadequate amount. And you can see the same grunge on here. This is whatever that is. It came off the potting on the board. But yeah, not enough ceramic caps in my opinion. And, you know, this right here, this is battery plus, and you can see another one of those studs came up. That's another one of these little guys right here. Came up. Yeah, and they just pulled right off the solder pads. They weren't really held down very good. But, yeah, this is all battery plus right here. And in fact, if I scroll down here, remember those pads out on the end of the logic board? Well, there was a stud right here that threaded into, and as you can see, it pulled right off. So you've got copper underneath the backs of the MOSFETs, and you can see it all the way down to about like there. But this is also reinforced by the logic board, which is a sucky idea. What they should have done instead was shifted all these MOSFETs that away a little bit, so they could put down some copper right here, you know, rather than just doing this. But they didn't. Instead, they reinforced it by doing it on the back side of the logic board, and well, that sucks. And you can see it comes around here. That's all still battery plus. And it goes all across this edge right here. That's all battery plus. All the way over there. And, of course, there's another stud that pulled itself up. And here's battery plus here. And then you've got a stud that then goes up to the logic board again. And then right here, yeah, that's the actual battery plus stud for bringing battery plus in. And it's, of course, ripped off and totally destroyed. Because that's how this works. You know, when you take that and you just solder down by this little area, and that's about the same size of a stud, by the way. It's like what's on a KO Pro, that same area. Well, this is what happens. You know, you torque on it a little bit, and they rip off. In this case here, this was done by depotting it with hot potting on there, and it still pulled it up. But yeah, that's the kind of problems that you have with metal core printed circuit boards. Now this one here is partly missing. Yeah, this is ceramic right here. You can see where the bonding was for the copper on the top of it. But yeah, there's a big piece of it missing. And yeah, see that? I can pick it all up. This is what happens. This is what happens when you have insufficient support on a metal core printed circuit board. The ceramic just doesn't hold the traces that well. And anything that's going to suffer stresses on it, like say a stud that's going to take a screw, well, it's going to have the potential of ripping up like this. And that's very much the case with KO Pro, and here it is on the Surron controller, and of course the Teleria did the exact same thing. And you know, here's all three phases, here's battery plus, and those are all ripped out. Battery minus survived. Let's see, is that one loose? I don't think it is. No, that one's still in there pretty good. But yeah, that's a common problem. Yep, you shouldn't do this. You should give your studs, your stuff you're going to screw into, stuff that's going to see stress on it. Yeah, look at that one. Completely lifted up. Yeah. Should give all that stuff plenty of support. So what really should have been done here is a piece of copper put across this whole entire area, and then the studs should have been soldered to that, so that none of this kind of lifting would have happened and tearing and stuff. That would have probably made that all survive, but nope, they didn't do it. So yeah, not a great design. You know, about the only thing I can say is a saving grace here is, like the Teleria controller, this was all potted, right? So it was a lot more rigid and beefy than, say, like the KO controllers, which are not potted, and they're still using the exact same idea. All right, so I talked about, I've got the board flipped over now. I've talked about this being battery plus up here. Well, it also runs all the way down here, across the backside of these MOSFETs, all the way down to here, to that stud. That's all battery plus as well. Or do I have that wrong? No, I don't think I do. That's all battery plus. Yeah, that's all battery plus, all the way through here. All the way down the backside of those MOSFETs. So, yeah, it's not super good. I would much prefer to see copper on here, and there's nothing. Yeah, that's not awesome. And, yeah, that's what it is. So, this is battery minus through here, and, yeah, you can see those 4 studs. So, essentially, from here to somewhere's over here, I guess, there was a jumper wire that went across the two. Forget how that worked exactly, but yeah, there was a wire that came across to there, and this is all battery minus through here. You can see ground. Hey, check that out. Anyway, again, that's all just, you know, copper on here, and then it's reinforced on the logic board. Of course, this part isn't. You know, you're just wholly depending on this copper down here to go to the low side MOSFETs all through here. And the only real place you have a current path is right around these 4 center holes. Otherwise, you're completely dependent on this bit of copper right here for all of your ground stuff, all your battery minus stuff. And then, of course, it tees off over here, the same thing. So, yeah, the battery minus down here is not awesome. Yeah, I mean, it's not like they didn't have room for it either. How hard would it be to leave like this as bare copper and to lay down a piece of copper that lays all the way across all this stuff, all the way up here, all the way up to there? You know, all these studs, they're all soldered down to it. It comes all the way across here, all the way up to there, all the way down to there. How hard is that to do? And, well, they didn't have it. Probably it's good enough because, you know, this is a fairly low power controller, but, yeah, I would much prefer to see copper reinforcing, and there's not. And, you know, like here's a phase. You're completely dependent on the circuit trace that's underneath the MOSFETs as your phase bus, and I mean, these are really close together, so that's not so bad compared to, like, say, the Teleria, which had larger gaps between them, you know, by a lot. So this isn't so bad. At least this current path is fairly tight, but still, you know, spread the MOSFETs just a skosh so you can put a piece of copper down all the way across here. How hard is that to do? But it's not here. So, yeah, that's pretty much everything I want to show about this Surron controller. Could it be better? Yeah, it could. The MOSFETs are not that great. Some stuff is a little weird, like using these single-sided, you know, single-channel gate drivers. So now you need twice as many of them. You know, they could have easily populated this with half as many chips and gotten the exact same gate functionality, you know, just with using dual channels so they can handle high side and low side. So there's things like that that are odd about this. And, yeah, not copper and all the studs just, like, coming up because they just really weren't supported very well by solder. Yeah, all that stuff is odd about this design. I can't say that I am particularly impressed with this power stage. In some ways it's better than the Teleria, and other ways it's way worse. Yeah. And of course, you know, you always have this problem. And like I've already ranted about, this is not how you do your studs down to metal core printed circuit boards, because you'll always pull up traces like this. Yeah, this is a problem waiting to happen, and here it is. You can definitely see that going on right there. And you don't ever want to have that. That's when you basically, whoops, sorry about that. That's when you basically throw away this power stage and you buy another one. Yeah, you could probably fix this, I guess, but yeah, it'd be much better if this was all one solid hunk of copper all across here, so it was all reinforced real nice, so you didn't pull stuff apart. Anyway, yeah, hope that helps some folks out. You enjoyed seeing the inside of a Surron power stage and logic board. And yeah, please like and subscribe and leave comments in my videos. Thanks a lot, folks, and take care.